Well, good afternoon, everybody. Thank you so much for logging in to our webinar, and we really appreciate you taking the time to do this. It's really encouraging, just looking at the numbers. We've got a really good number of people who've logged in online now, so thank you so much. We're bringing this to you from Composite Integration. We're presenting from our factory in Cornwall in southwest England, and my name's Tim Searle. I'm the R&D director, and this is next to me my colleague Richard Bland, the technical director at Composite Integration.
Good afternoon, everyone. And everything we do at Composite Integration is about making world-class composites. Although today's topic is really based around future aerospace composite, we have a significantly wider perspective by working across several sectors, including wind blades and large marine structures. And there's much to be learned from working across these boundaries, and some of this is going to come out in our presentation today.
So we hope this will be useful, informative. We have scheduled about 45 minutes for this. We'll speak for about 30 minutes, and we'll allow the remainder of the time for your questions and, importantly, your comments, actually. So do think about these, put them in the Q&A part of the chat, and we'll ensure that we allow as much time as possible to answer these at the end.
Okay, so let's get started. We'll discuss what this webinar is about and how it relates to what we're all trying to achieve in the manufacture of composites.
So to our title, let's move my notes across there. Does liquid resin have a role in future aircraft structures? Well, clearly the simple answer is yes. Many of you are working on this on a daily basis, but we all know there's a challenging context here in which we are working. I'm not sure that we need to rehearse the specific challenges of aerospace rate production here. We've covered this in the paper, but of course it is covered very well articulated with clarity with lots of our colleagues, industry workers, and so on. But I think it's still worth just summarising the challenges, and perhaps worth noting that other sectors are working with similar challenges. You see, wind blades are getting bigger and bigger, we know that, and as a result quality is becoming much more important. And of course takt times in the production of blades is very important too. Mentioned already and mentioned before, but aerospace structures, as you know, are requiring much faster takt times. But in addition to rate, we're aware that verification of quality, and particularly verification of some of the new breeds of 2K resin systems, particularly on ratio, are becoming more important. And in addition, working with very challenging fibre forms that the aerospace industry demands. And our marine customers are building more ambitious structures. Certainly, we're working on those as we speak. But they require cost savings, again quality, but also weight consistency becomes very important for our marine customers. So in all these sectors, wind, marine, aerospace and others, we are constantly being asked to help our customers build faster, cheaper, with a critical eye on quality, and of course to do this in a more sustainable way. And so the question that confronts all of us is, can we do all four of these things? And traditionally, this seems the impossible equation to solve. We're all aware of the capability of a prepreg and delivering high quality parts, but also we're aware of its cost, some time consuming limitations, and in many cases, the dependence on the autoclave. But the benefit in working in several sectors, for example, We can apply the learning from very thick UD spar caps that are common in our marine and wind sectors, and apply this to aerospace infusions where perhaps we're a bit more preoccupied with quite impermeable fabrics and things that are quite hard to make, albeit because the mechanical properties can be very much better.
There have been significant changes over the last decade or so in terms of these manufacturing requirements, but also in the technology available to solve some of these problems. And in the past, projects have existed where good parts could be made, but certain elements of how that was achieved wasn't always well understood. And in truth, we still come across a number of myths which have to be removed by a clear understanding of underlying science. So in the past, we think our industry has often got away with certain ways of making composites, but now the demand for rate and quality really changes that equation.
But before we jump into some of the detail on how that works through, just perhaps a trip down memory lane for some of us. In the photograph, you can see some 20 years ago, the development infusion of a 40-meter wind blade. This actually is an AL40, which was from Aero Laminates, which was then acquired by NEG Micon, which was then acquired by Vestas. Years ago, we did this. A lot of buckets, a lot of hand mixing, but actually things worked reasonably well. We did, at the time, we measured flow rate, so we knew how much resin was going into the part. But on the whole, these infusions were very successful. At the time, blades were much smaller than they are today. A 40-meter blade versus the sort of 115, 120-meter blades that we're currently working on. At the time, we thought this was a huge infusion, but a lot of the parameters seemed to work. We didn't at the time get in any way obsessed or worried about degassing of the resin. We had some quite clever strategies to enable the resin to flow into what was still, at the time, quite a big part. And thousands of blades were made like this. You can see, if I haven't mentioned this already, that this is largely a wood and carbon blade with glass skins. But in this, we needed to scale and we needed to automate. And this really did pave the way for what we call direct infusion.
So the requirement to manufacture ever larger and more complex structures of a mixture of monolithic and sandwich laminates, with in some instances several tons of resin mixed on demand, led us to developing more automated mixing and delivery processes, and really starting to question which variables impacted the quality of those processes. The example you see in the picture is a 32-meter boat infused from a single injection machine in 4.5 tons of resin in around 5 hours, for example. So this examination of these quality variables, it encompassed not just the general infusion process, but the effects of materials, of tooling, and of the equipment itself. And it was clear that understanding these variables, fundamental to quality and then building the capability to control them, it was really vital. So getting these large infusions wrong isn't an option. The cost is significant. So understanding those variables and getting it correct is really important. And part of that journey was evolving the next generation of meter mix equipment, designed not just to mix and dispense materials, but to condition them carefully prior to the infusion, to infuse them directly into the tool with no intermediate stages, to get rid of buckets and hundreds of pipes, and to have extremely accurate control over pressure, flow rate, ratio, temperature, all whilst being able to feed on demand at fully variable flow rates ranging from almost zero right up to, for example, 30 kilos per minute. So verification and data collection really evolved during this sort of 2000s, 2010, 2020 period, and it led to very large data sets being created which we could analyze. So if we look at one of those elements of the process, which we know is critical to part quality, and that's the resin inlet pressure, we can see the chart on the next slide is really typical. So this chart's taken from a typical large-scale resin infusion. And the infusion machine is capable of varying and controlling inlet resin pressures really accurately. So we can see during the startup phase of this infusion, if we look at the red line, we start increasing flow rate until we reach an exact programmable resin inlet pressure, and in this case that's around 900 millibars. We can vary the ramp of that startup phase, we can play endless tunes on it. But the ability to control this exact resin inlet pressure, whilst all the other variables around are also under control, and in the case of flow rate constantly changing, it's a unique ability contained within the Siject equipment control systems and software algorithms. These systems also compensate during process for events which occur on the fly as the process as the part is being infused. For example, another resin inlet being opened or closed, which creates a pressure variation, or part permeability variations as we go from monolithic to chord sections, for example. So controlling these leads us to really true automation of the resin delivery into these complex parts. And although this graph is for a large wind turbine blade, the principles and requirements are exactly the same for a high quality, high VF aerospace carbon epoxy component.
So I think it's worth just appraising what's achievable now. Where have we got to with these liquid resin processes? Well, we've mentioned this already to some extent, but wind blades approaching 100 meters and beyond with 24-hour cycle times, with consistently improving quality is now a reality. Marine structures where direct infusion is more or less routine, they're better working environments, the quality is improved, and importantly, weight consistency is improved as well. But our aerospace applications, where we can show clearly the quality of resin-infused applications. The part in the middle of the slide is an external panel of a thrust reverser door. It's made by Resin Infusion with RTM6, with Sartex multi-axial carbon. There's a bronze mesh lightning strike, you can't see it because it's behind the paint, incorporated into the laminate as well. And in this particular case, the layup with dry material was simpler and more productive. Aerospace grade laminate quality was evident, with fibre fractions just shy of 60%, and a void content that's now becoming so low that it's actually challenging to measure, and quite often the reports get sent back to the lab because we need to try them again because the quality is so good. And in addition, there's a significantly lower overall manufacturing carbon footprint without the use of the autoclave. And this is an example where it's very viable as an alternative to pre-preg. The principles of direct infusion transfer well across sectors, but I think much of what we've learnt in recent years is now finding a really strong foothold in aerospace infusions.
And we've talked about infusion a little bit so far, but when it comes to traditional medium and high pressure resin transfer molding, historically things are quite well advanced. And we might, for example, look at the propeller blades produced by GE Doughty, and for several decades now, that have historically been incredibly successful. We'd also mention the 17-meter C-spar for the Wing of Tomorrow, manufactured by GKN, using Siject RTM injection equipment under a very controlled process. It's a logistically remarkable project, actually, from very large multi-part heated invar tooling, and demonstrates a significant step in what's actually possible from RTM in terms of quality, size, and tooling capability. The future challenges for the aerospace industry, however, are about rate and consistency. And if we have a little look at the picture on the right, we can see a manufacturing cell designed and developed by Composite Integration for very high volume manufacturing requirement. So that cell, it's a fully automated cell utilising twin stage hydraulic presses. It's a hands-off operation. It runs 24/7 pretty much. I think an hour for maintenance each day, each 24-hour period. The part is a complex preform. It contains cores, large metal inserts, it has noodles, and it has multiple fibre types, both wound and unidirectional. The tooling is a multi-impression tool. It makes 4 components at once to really improve productivity. It's heated, it's running around 120 degrees C with snap cure epoxies. And those materials, we run continuous verification of all the materials in the process, including, for example, real-time measurement of the 2K mix ratio, which is so critical. Part of all that cell, we do a lot of data acquisition, and remotely we can draw in that data in real time, and we do analysis to help continue to optimize that process and deal with any issues that come up. So this cell is one of 6 that's installed in one factory in Europe, and currently producing more than 10,000 really high quality, high VF, low void content components every single week. So more than 10,000 a week.
So we've been working very hard on quality, and without that, the other 3 requirements that we've mentioned become a bit questionable. In this slide, we've got a typical spar cap component made largely from UD carbon. It's about 120 millimeter cube that we've cut from a sample, and it's infused. And we've spent here we go. We've got it with us, so try not to drop it. But and on the right hand side, perhaps a much more contrasting, skinnier aerospace part, where the effort that goes into this to ensure that we can infuse this successfully at the right sort of quality, there's just as much effort that goes into ensuring that we can faithfully produce very, very tight, high tolerance radii on liquid resin infused parts. And so, there's a couple of contrasting applications there. But I think in all of these cases, we need to be really clear on the key factors that contribute to success. In the example of the cube here, the spar cap, what was required was a very firm grasp of the implications of permeability of a UD material, a UD carbon. This was infused with a fibre fraction of around 58% and a void content that is very, very small, probably less than 0.5%. So with this in mind, what are some of the key factors that contribute to success? And by the way, you can just see the micrograph image taken directly from this on that side face indicated in the picture. So what are the factors that contribute to success?
And over the last decade, or really starting actually around 2013, 2014, we started working in conjunction with multiple aerospace partners, and we've delved into a large number of the questions and the variables to sort of really try and deeply evaluate their particular and independent impact on manufacturing quality. What this has resulted in is a solid understanding of which basic principles must be in place in order to produce aerospace quality components by liquid resin moulding processes. There are dozens of variables, but what we want to discuss in the next section is just sort of 5 of the key principles that we think are really important to understand well.
Now we're going to present 5 to you. You may have comments, questions. You might not agree, but here are the 5 things that we think are important. I think firstly, top of our list is it really helps to have a quality environment where you and your colleagues can build composite early, can build it often.
Sorry, Tim. Apologies.
Jump the slide, you can have that one in a minute. Where we can try things, you can build, measure, and analyze quickly. You can make something, you can get it under the microscope ASAP. But of course, that does mean you need experienced people who are prepared, allowed, and equipped to make a judgment on the quality and the effectiveness of what it is that you are, what is in front of you to build. The trouble is, in our experience, it seems that people don't often seem to do this. Here's a typical, and albeit, yes, it's a rather straightforward example. Perhaps it's flat and a little bit boring, but this was part of a study that we did for a marine customer of ours. They had a particular laminate and resin combination for a very, very large and challenging part. The infusion required multiple inlets from our Siject 2. It was quality and VF critical, but a strategy for the infusion was needed. This picture is taken mid-infusion. You can see these are two 303 meter samples. Actually, the one on the left is a little bit shorter, with multiple pressure sensors and resin inlets, and of course thermocouples. The point is, when the tests were complete, it taught us and the customer what the strategy needed to look like for the infusion. And to give you a sense of scale, the resultant infusion on the part was a couple of tons of resin and took about 12 hours to infuse. So with a couple of days of informed setup, a day or so infusing with the customer, a little bit of analysis and follow-up of the reporting of the data we gleaned from this. This is an incredibly instructive and good use of time. Similarly, and again, it may seem very obvious, but secondly, we would say accessible, practical laboratory measurements are absolutely key. This might seem obvious, but surprisingly, again, it's not always the case that the right equipment is available in the right environment. So, for example, here we have some of our in-house equipment. On the left, we have a fabric characterization press, so that we can look at accurate ply and laminate thicknesses under a variety of different pressures. So we can look at a single ply thickness, we can look at a thick stack to see how that behaves, and we can do that wet, and we can also do it dry, because we know that behavior is subtly different. And for the keen-eyed amongst you, you can see that the 563 is actually the pressure in millibars that laminate is seeing under test. On the right hand side, we've got is disassembled the picture, and it's a piece of work we've been looking at for a little while now. But this is our permeability rig, so that we can look at through thickness permeability on challenging laminates to either resin transfer mold or infuse. And of course, those laminates that are a little bit more permeable and easier to infuse. So this is a little bit new for us. We're preparing to publish the data on this, but the results we get from this are incredibly promising. That whole assembly goes inside that aluminium barrel, and then we can put a surrogate or an actual resin through that to look at the permeability performance of the plies under examination. And we can go single plies or laminates up to 50. So it's real world stuff, and we can generate this data really quickly.
Third area to look at, really, degassing and degassing measurement, and this is a topic that's been in our consciousness for a very long time, and much has been talked about it, and an awful lot of questions have been asked about it. What we really needed to do was to be able to qualitatively measure how degassed a resin is. And so that was really important for us, and a lot of work has been done on the void content and the mechanical properties of laminates made from degassed materials, but there's been little or no capability to measure how degassed the material is prior to part manufacture. What typically happens is a resin will be put at a temperature at a certain vacuum level for a certain period of time, and there is a presumption that has successfully degassed the material. So our determination to resolve this resulted in 2 years of work to develop a sensor capable of measuring the quality of degas of a resin system in near real time. And we've validated this through hundreds of trials, both internally in our labs and with our customers in the real world. So this technology is actually now incorporated into our wind sector equipment, and the need for it was driven by them. And it provides a go or no-go indicator that the quality has to reach a certain threshold before we can begin a large wind blade infusion. And if we look at this next slide, here's some of the equipment that incorporates that technology. And the image on the left is taken from the top of the bigger of the 2 tanks you can see on the machine. The tank's around 2 meters tall, and there's around 1.5 meters from the top surface of the resin to the bottom outlet fitting you can see in the bottom of that tank. And we can see from the clarity of that resin, it sort of tells us, our gut feel is that that's a really well degassed resin, and in truth we know if we've got that clarity it's pretty good. But what we also get now from our measuring system is that we can see the rate of improvement of that degas over time, and we can reach a threshold at which not only does the resin look really clear as it does in that tank, but actually we know that it's properly degassed and will make a high quality laminate when used.
So in addition to this, and fourthly, a key factor is that we need a really good understanding of the process pressures. So the graph that we've put up here is a classical resin inlet pressure curve for a low viscosity resin infusion. We've seen something similar to this already, but actually if you go to the left-hand side of the graph, well, you can see that the pressure sensor that is, in this case, will be close to the resin inlet, the supply of resin into the part, and would be feeding back to the Siject, is actually at atmospheric pressure. That's because we haven't turned the vacuum pump on, and we've simplified the graph. But as soon as we turn that on and establish a vacuum in the part, you can see that that pressure nicely goes down to what would be a nice, a decent vacuum. This is closer to what we would find in an aerospace infusion, this particular graph, with a single component, really low viscosity resin system. But let's just have a quick look at some of the key characteristics. Well, the first thing that we usually notice is that there is a classical drying sort of bump as the pressure rises. This is as we will have applied temperature to the part. So we've done a vacuum check, we've now heated the part up, and we've applied pressure to the heat to the part, and as it heats up we see the sort of vapors and things start to move away, and we get a short rise in pressure before it returns to something a little bit lower. Part 2 is where we have the initial resin inlet. We have can be rate controlled, and we can build we can build the resin set point and program that in, typically between 800 and 900 millibars. So that's our set point, and then number 3 is the end of the infusion. And this is an important bit, because this is where, with particularly low viscosity systems, we start to reduce, the pressure can start to reduce if it's allowed to bleed on. Not so important with, not so likely with net fill infusions, but actually if we allow this pressure to fall a bit, we can gain a 2–3% fibre fraction. But the danger is if we let it fall too much, then the laminate does become much more susceptible to porosity. So to our 5th point.
Our fifth and final point of discussion. We've touched on the ability to collect data from equipment, but technology now used in everyday Siject production equipment allows the secure collection remotely. So here in the office we can collect data through a secure cloud system. We can do that for a wide variety of sensors and systems on any machine anywhere in the world in real time. It's incredibly useful for process analysis and optimization, and in collaboration with several customers, we collect that data along with them or on their behalf. We analyze it, and we can go back and support with process optimization. And we can identify variability which previously hadn't been identified by the customer. At the moment, we're using human intelligence, or HI, to work through these data sets, but we are examining at the moment the use of AI to try and speed up that process and give us a little bit more insight into some of these very large data sets.
So, by way of summary, these are some of the things that we've been putting quite a deal of effort into recently. Of course, building on some of the fundamentals that have gone before. And we present these to you as food for thought and food for discussion. There's a lot more we could say, but before we conclude with the final slide, I'm just sort of looking to my colleagues. I think we've got some other questions coming in.
We've got a couple of questions that we've had before the webinar have come in.
Yeah, brilliant.
But if anyone wants to get some questions,
do throw those questions into the Q&A, and we'll get to the few that have come in already. But just by way of a closing slide, we've come back to this particular example. I think what we've aimed to do is to show the depth of work that we've done over a period of time. Just recapping on the thrust reverser door in the picture, made without an autoclave by resin infusion. The productivity was improved significantly, and the carbon footprint was reduced by about 60%, and it did show a weight saving over pre-preg. I think over several sectors with multiple complex and very often challenging infusions, competing with pre-preg on quality is now achievable. High fibre fractions, low porosity levels that are challenging to measure do give us real confidence in what is possible. As far as costs go, we can't delve into specific projects, but generally speaking, working with raw materials that are cost effective, lower cost than pre-preg, and obviously the cost of storage and autoclaves without those expenses. I think we'd all acknowledge that with some very thick dry laminates we can do significantly less debulking. So operationally speaking, we're familiar with laminates of perhaps in the order of 100 millimeters that can be put down in dry material without any debulks.
So from looking at the presentation we've given today, one thing that's clear: quality is a non-negotiable in the aerospace sector, and rate is the key challenge that we're facing, or the key driver. So having demonstrated that we can achieve that aerospace quality in liquid processes by the control of these key process variables, the key next step is to add rate from existing knowledge of higher volume direct infusion and low, medium, high pressure RTM systems. So adding that automation will help us to reduce the costs. It's going to deliver competitive production parts and allow us to accumulate the large quantities of data that we seriously need in order to move forward the future of liquid resin moulding for part manufacturing in the aerospace industry. And if we look among many of the examples we've talked about, the example on this slide meets all of our requirements, our manufacturing requirements, meets or exceeds them. So to ask the question, liquid resin, does it have a future in aircraft structures, the title of our webinar, we would say absolutely yes, it really does. And what we need to do is challenge the industry to really get involved in the next stage of development to identify parts and really start to push those boundaries of manufacturing and save the costs, save carbon footprint.
Great, Richard.
So thank you, Tim.
Good. I think just a little comment flashed up on my screen from, I'll try not to single too many people out, but Chris Little, hello. I remember working with you on those blades all those years ago, and I think your comment was does this technology have a future? Well, you're saying yes. I mean, we've worked together on this in the past, so good to have a thumbs up from you, Chris. And yeah, so we got a few questions that we can. I know one that often comes in, Richard, is about what other elements of machine control would we consider to be important. I think that's perhaps come up. I don't know whether you want to talk to that one.
Yeah, I mean, there are several, of course, but we know temperature is critical to all these processes, and consistent control of temperature from the material storage element right through the entire process into the tool itself. So that temperature control is really, really important. And I think one of the other areas that's quite interesting is the aerospace sector is looking at some of these challenges around single part materials. So looking at the two component question for aerospace has always been around how can we verify that mix ratio. So not only the ability to measure in real time and accurately report on that and collect that data, but it's also important in the control systems that, you know, all of these processes, we make bigger, more complex parts. The flow rate will vary continuously, and we have in-process events. And what has to happen is not only do we have to maintain constant inlet pressures throughout that, but we have to be able to maintain accurate ratio within a very small tolerance through those step changes of speed or flow rate. So I think those are the things that we've worked incredibly hard at building into these systems, and are absolutely proven as capable in both small and large structures.
And we hear it regularly, don't we, from our aerospace colleagues, customers, who will say, if it flies, it has to be verified. You know, if it's a two-component system, and what does that look like? I am just looking over my shoulder at a couple of questions, but there are a few that are coming in, and I don't know whether we just.
Yeah, we've got one from Anne Cantor.
Yeah.
In near term, what aircraft parts do you foresee transitioning to resin rather than pre-preg?
That's a good question. In near term, what aircraft parts do we foresee transitioning to resin rather than pre-preg?
I'm not sure there's a specific answer to that, is there, Tim? I
think one of the challenges that we have to measure that we haven't discussed specifically here is the way that we can manufacture appropriate preforms and hold shape on what are sometimes quite complex parts with rib stiffeners and so on. And we know that the industry has wrestled with do we choose resin infusion, which has some significant tooling benefits and has an elegant simplicity to it, and we've shown that it works in terms of quality. But when the challenge comes to making something that has some geometry that needs either cool plates or some further registration of those parts, that becomes a difficult question between resin infusion and resin transfer molding. I think I might suggest that, you know, we need some technical confidence here, and the way that we often demonstrate that this works is by building demonstrators that show the feasibility of what is possible, because we've done that quite a lot. So, Abby, that's not a direct answer to your question, but I think if you take into account the complexities that we've just raised, I think you know, there's an awful lot of potential here. Yeah, there's a.
What should I take? The next one from Christopher Silver.
Yeah.
You know, the next question from
Hi, Chris.
Christopher Silver. Hi, Chris. Is
Other Chris.
You know, is there a general time for degassing epoxy? And the honest answer to that is no. The things that affect rate of degas include temperature, so its viscosity, and how thin a film we can form it over, and some of the nature of the epoxy itself. So we do find there is an amount of variation. We can obviously do things to increase the speed. We can incorporate sparging into degassing, and we've actually been testing various sparging methodologies and have a rig in the lab to actually evaluate their impact on how quickly degassing can occur. But in terms of an exact time, it does depend on a number of other variables, I think.
Yeah, and I think volume, the volume that you're trying to degas, of course, is obviously important. If it's something like 1,200 litres of epoxy for a wind blade, that's going to take some time to compared to a 4 to 5 kilogram or litres of a small aerospace component. I think we're seeing good results reported on these smaller quantities, easily inside an hour, but actually for these bigger quantities, it can be a few hours. But I think ultimately our answer would, not to sidestep your question, Chris, but the answer is to if you have what is needed is the objectivity to say, when is it done? When is it cooked? When is it degassed? And actually this is the sort of thing that we've been trying to offer. So, what else?
We've got another question from Gabrielle Bedini.
Hi, Gabrielle.
What is the appetite for part manufacturers to handle chemicals rather than pre-preg?
Say that question again.
What is the appetite for part manufacturers to handle chemicals rather than pre-preg?
Because we're using liquid resin systems, and I think that's a really good question, and this came up when we started working in the wind sector. One of the very first demonstrations we did, and one of the problems that the wind sector was having was epoxy sensitization. And actually, as we went to demonstrate a direct infusion process to one of our large wind OEMs, the key was that there was no exposure to material. It went from a closed container through the equipment and directly into a closed mold. So whilst, yes, in theory there is liquid systems in the building, the reality is the exposure to that liquid system is zero. People don't touch it in any way, shape or form. It passes from bulk through equipment and into part and is cured. And actually looking at how cured the part is before it even comes out of the tool, it's then assessed to determine whether there's any residual risk from fraction under cure. So we even look at 90% cure. So it's a really good question. The health and safety side is really important, if I've got the question right, and apologies if not.
I think what I just might add to it, so it's perhaps a little bit obvious in terms of logistics, is that this handling of these liquids in a much more mechanized, automated process is part of the maturing of the industry. It's part of the maturing of turning this into something really much more sophisticated. I think we've got about 30 seconds left, haven't we, Anna?
Yeah.
So have we got one last question quickly?
I think we'll probably be tight for time, but we will. What
we'll do, guys, any questions that are left, we'll go back and we'll write to those people and we'll answer them personally. And we'll also contact everyone who has attended today. So thank you ever so much for attending today. It's been a pleasure to present to you all.
Yeah. And thank you from me too, and we look forward to seeing you all very soon.
Thank you very much, everyone.